Le Chatelier's principle states that if a dynamic equilibrium is disturbed by changing conditions, the system will adjust itself to counteract the change and partially restore equilibrium. In this first example, we're going to explore how temperature can shift the equilibrium of a system. So I have here a beaker full of liquid propane at negative 42 degrees C, and then an ampule of nitrogen dioxide gas at room temperature. You can see that when I cool the nitrogen dioxide in the propane bath, it goes from deep orange to clear, as it first dimerizes to dinitrogen tetroxide, which is most favorable at this temperature, and then supposedly freezes solid. I think that's pretty cool. You can see that when I take it out of the bath and warm it up, we get that lovely red-orange color back. Pay no mind to the beautiful blue droplet at the bottom of my ampule, by the way. This is definitely totally pure nitrogen dioxide with no contamination. So what we'll do next is subject the equilibrium system inside the ampule to a range of some more reasonable temperatures and watch how it shifts. The first beaker is full of ice at about 0 degrees Celsius, and we're going to see the color of the gas in the ampule lighten slightly. It's a bit subtle, but it's noticeable. Since the reaction going from the dioxide to the tetroxide is exothermic, we can treat heat as a product and, by quote-unquote removing it, drive the reaction forward. This is going to leave us with a mixture enriched in the tetroxide and depleted in the dioxide, just as Le Chatelier's principle predicted. Now I'm just warming the sample up to room temperature in a normal water bath, just to reduce the risk of heat shocking the glass and overexposing everything as well. Now we're going to move on to the hot water bath. And this is a real striking color change. The water's about 70 degrees C, and at higher temperatures, the formation of the monomer nitrogen dioxide is heavily favored. You can see that by the gas in the ampule darkening like that. Now we're going to look at the effects that pressure has on the equilibrium of the same system. This just happens to be a great reaction for both demonstrations. What you'll notice is that either side of the equilibrium has a different number of moles of gas, so increasing the overall pressure of the system will cause it to shift to the side with fewer moles and vice versa. Note, however, that this has nothing to do with the partial pressures of the reactants or the products themselves. I have here a sealed syringe filled with about 40 milliliters of the same equilibrium mixture as before. When I suddenly increase the pressure, it gets darker, but then gradually begins to lighten again. That initial counterintuitive change in color is due to the temperature increasing from compressional heating. But after letting it sit for a minute and come back to room temperature, you can see that the gas gets ever so slightly darker at low pressure and ever so slightly lighter at high pressure. Finally, let's look at the effect that concentration has on an equilibrium system. Chromate and dichromate ions exist in equilibrium with each other in aqueous solution, and their relative concentrations depend primarily on pH. Since H+ appears on only one side of the equation, we can alter the dominant species present in solution by adding acid or base to a solution of these two ions. Here I have a solution of potassium dichromate and water. When I add some sodium hydroxide, H+ ions are removed as the pH increases and the equilibrium shifts towards the formation of yellow chromate. When sulfuric acid is added, once all the hydroxide is neutralized, an excess of H+ shifts the equilibrium back towards the orange dichromate. You can see that the final sample is actually even darker than the initial solution, despite being more dilute, because the low pH favors almost exclusively dichromate. Well, that is the end of my deep dive into Le Chatelier's principle and chemical equilibrium. I had so much fun doing this that I completely forgot it was for extra credit. Thanks for watching.